Today I'll be talking about generalized Hamiltonian cycles, and I will somehow show you some overview of known results and some new results rather than just showing like one result with complete proof. So there will be like more results, and maybe I'll show you some sketch of the proof which are short and somehow nice, has a nice nice tricks in it. So what I will start with, so you probably know what is Hamiltonian cycle. If not, so here's a definition. It's a cycle in a graph which visits every vertex of the graph. So that's a very simple definition. And the Hamiltonian cycle has been studied fairly high. So like there are many results concerning Hamiltonian cycle, and it's known that decide whether graph is Hamiltonian, it's NP complete, so it's really hard problem, and there's no practical characterizations of Hamiltonian graphs, so it's really hard problem. Therefore, like some people try to generalize the notion of the Hamiltonian cycle, or just maybe worry because instead of Hamiltonian cycle you might look for Hamiltonian path, or even more hard is to look for Hamiltonian connected graphs, which means that there is a Hamiltonian path between every pair of vertices. So it's even stronger than Hamiltonian cycle, because if you take two vertices which are adjacent and there is a Hamiltonian path between these two vertices, you get a Hamiltonian cycle. But I want to like go in details. There are so many notions. So what is like the research concerning Hamiltonian cycle? There are many areas, and like maybe the first well-known is the degree conditions. Like by degree conditions, I mean like you probably know Ores lemma, which tells that, or Dirac's theorem, if you have two vertices of high enough degrees, like the sum is high enough, then the graph is Hamiltonian. In fact, it is if you have for every pair of vertices the sum of its degrees is at least n, then it's Hamiltonian. And it has been by the Ores lemmas about the degree conditions tell us that if you have, like, let's say it's not every pair of vertices has this satisfy this condition, but there is a pair of vertices which are not non-adjacent and the sum of its degrees is at least n, then you can add h in this graph, and the resulting graph of course will be Hamiltonian. But if the original graph wasn't Hamiltonian, then the resulting graph won't be Hamiltonian anymore. So like adding this h won't destroy the condition whether the original graph was Hamiltonian or not. So therefore, you can define a closure of graph. That means you can add h between every pair of vertices which satisfy this condition, and the resulting graph will be called closure of this graph. And it's true that the original graph and the closure has Hamiltonian cycle if and only if. So, but I won't go in details. The another area of research is local connectivity. It's local connectivity is you say that vertex is locally connected if its neighborhood is connected graph, and you say graph is locally connected if every vertex is locally connected. And the local connectivity was really studied in our department really well, because my boss Denis Ratchet proved that if you have a locally connected vertex in a claw-free graph, then if you take this vertex, put all possible edges between the neighborhood into a neighborhood of a locally connected vertex, then again it won't change the existence of Hamiltonian cycle. I mean, like after adding these edges, of course, if there was a Hamiltonian cycle, there will be, but if there wasn't Hamiltonian cycle, you won't create any by adding all edges into a neighborhood of a locally connected vertex. And again, you can define a closure of this graph, and it behaves similarly to this first closure defined.
So you simply make a
clique
neighborhood as a clique.
Yeah, and if you do this like recursively for every locally connected vertex, you get a closure, and it's true that the original graph and the closure has Hamiltonian cycle if and only if. But the graph has to be claw-free. It doesn't work for like all graphs. Then the forbidden subgraph, it's there are because you might study like which forbidden subgraph implies existence of Hamiltonian cycle. There are many theorems, and I think there exists a complete characterizations of forbidden pairs of graphs which implies existence of Hamiltonian cycle. And the last condition, toughness condition, I will be talking about a bit more. So I will skip to the next slide, because you will see what toughness and tough condition is later on, because the definition is not that easy. But yeah, let me say a few words about how to generalize the Hamiltonian cycle. So there are many ways of doing it, but for example, like two-factor is one possible way of how to generalize Hamiltonian cycle. Actually, two-factor is just spanning subgraph such that every degree of every vertex is 2. So clearly, Hamiltonian cycle is a two-factor, but two-factor can be collection of cycles as well. So it's, let's say, more general than Hamiltonian cycle. Then we can dominating cycle is or you can put a path here, or dominating path is so like dominating cycle is a cycle such that every vertex is either on the cycle or is connected to the cycle. So of course, like Hamiltonian cycle is dominating cycle as well. And the other way how to generalize is K-walk and R-Trestles, which I will be talking about. So the definition will be, I will say a bit later. So what now? So this is a definition of a K-walk. So K-walk is in a graph is a spanning closed walk which visits every vertex at most k times. So by walk we mean like sequence of vertices and edges, and you may repeat vertices in the walk and edges as well. So you can use one edge or one vertex more than once, and if you have a K-walk, then at most k times. Yeah, it's closed. It should be closed. Close. Then you start and end in the same vertex. Yeah. So if the k is equal to 1, it's Hamiltonian cycle, because you have to go through every vertex and at most once and exactly once, so it's a Hamiltonian cycle. So this is an example how a two-walk can look. You can see like you can have the graphs can be only one connected because you might use this edge twice, so it's fine. So, and like the last definition I promised is the definition of toughness. And toughness is defined as a minimum of a fraction, where here you have a size of a set, and down here you got a number of components you get when you remove such a set from the graph. And you take a minimum overall possible non-empty subsets for which you get at least 2 components. So it's similar to a connectivity, but it's, let's say, it's more refined, it's more precise, because therefore you can see this example, like if you try to go through all possible subset of vertices and always count this fraction, like number of the vertices in the set and number of components you get, then like the minimum you get when you remove these 3 vertices, you get 4 components, so therefore the toughness will be 3/4. And I didn't mention, if the graph is complete, then the toughness is infinity. It's high enough. So how is it related with the connectivity of a graph? So clearly, if, let's say, the graph is t-tough, or has a toughness t, then the graph is at least, let's say, 2 times t and rounded up to the nearest integer connected. Why? Okay, let's say the graph is 1 tough. So it means that in the worst case, if you remove only 2 vertices, you can get 2 components at most. If you remove, let's say, 4 vertices, you can get at most 4 components, but like clearly there won't be any smaller number, like the graph can't be one connected, because if you remove 1 vertex, you get at least 2 components, so therefore the toughness will be at least 2. Yeah, is it clear? Yeah. So, and yeah, so and the opposite implication can hold, because if the graph is, let's say, really high connected, so the connectivity is really high, then the toughness can be arbitrarily small. And why? Example of such graphs is complete bipartite. For example, if you take, you know, like one part and the second one is much bigger, then the connectivity of this graph will be the size of the smaller set, but the toughness will be, if you remove these vertices, then you get this number of components. The toughness will be size of this set divided by size of this. So clearly the toughness can be really small, but the connectivity can be high. So it's more refined than connectivity. So what can we say about the toughness and relating to K-walks or Hamiltonian cycles? So
when you say 1 over K tough, then toughness is at most one?
Is at least 1 over K.
Yeah.
Yeah. The toughness is at least this number. If we say 1 over K tough, then we say that there is no set which will violate this, for which we get less than this number, like this number will be smaller. Because if you take, let's say, graph has a toughness 4, then clearly you can say this graph is too tough, because the toughness is higher. But if the graph is, yeah, that's really it. So here this is a necessary condition for existence of a K-walk. So if the graph has a K-walk, or even if it works for a K equal to 1 for Hamiltonian cycle, so the proof is really simple, because, for example, here's an example of a 2-walk in a graph. Then by induction, you can prove it by inductions. By removing one vertex from the graph, you can get at most 2 components, because there is this 2-walk in this, and it must be at least these edges in it, so you can't get 3 components if it's 2-walk. So if you remove 2 vertices, you can get at most 4 components for a 2-walk, and so on. So still this fraction if K will be equal to 1, K will be equal to 2, is at least 1 over 2. So it can't be worse. So if this would be a Hamiltonian cycle, then the graph has to be 1 tough. So go on. So now, before I want to talk, so this was a necessary condition for existence. So if you want to look on a opposite implication for sufficient condition for existence of K-walks in a graph, then there is one, or there are maybe 2 of them. So, but to show it how it works, let me define first what is a K-tree. K-tree is a graph is a spanning tree. It's a tree which contains every vertex of maximum degree at most K. So later on I will show you how it's related with a K-walk, but first I will show you a really simple proof of this theorem from Wien, which tells us sufficient condition for existence of a K-tree in a graph. And it says if the graph is 1 over K minus 2 tough, then it has a K-tree. So the proof is, let's say, as follows. So assume like a contradiction, we have a contradiction. So assume we have a graph which doesn't have a K-tree. So in this graph, choose a tree, not necessarily spanning, which has maximum degree at most K. So let's assume this is my tree, which is not spanning, and has, for this while I will show it on the example for K equal to 3. So let's say this is a tree with maximum degree at most 3. And it's not the whole graph. There are some vertices which are not in the tree. So clearly, there is something outside. So there must be a vertex in the tree which is connected to a vertex which is not in the tree. So let's say this is this one. So this vertex must have a degree 3 or k in general. Because if not, then I will add one more vertex, I get a bigger tree. So clearly this vertex has a degree 3. So now remove this vertex from the tree, you get 3 components of the tree. And now, so clearly we got 3 components of the tree, but in the original graph G, there are some edges joining these components of this tree. So first, assume there is an edge joining one vertex of degree less than k, and the other vertex is less than k as well. So this cannot happen. So what if it happens? So let's say there in the graph is this edge, so clearly we can add this edge to the tree, then remove one of these 2 edges, and then we can join one more vertex to this tree. So it's a contradiction. So this edge cannot be in the graph. So only in the graph there can be edges such that one of its 2 end vertices has degree k in the tree. So now we will construct a, let's say, set of vertices from the tree such that this will be in the tree, and all these vertices such that there are edges between components. One of them must have a degree 3 in the tree. So this vertex we will add to a set. And again, similarly this one, or we might this one as well. So like there are some rules how to define this set, but I hope it's clear how it's defined. So now assume that this set, because like again, like if we will continue and remove this vertex from the tree, again we get 3 components, like this one, and the rest. Again, there can't be any edges joining these 3 components in the graph unless the end vertices have degree k. Otherwise we can add these edges and have smaller degree here. So finally, if we take, so we have these vertices, let's say, somehow defined, and if we take a maximum number of these vertices, then what we will get is a set of vertices of the tree which have degree k, and after removing these vertices from the tree we get some number of components. But what we will true as well, that if you remove these 3 vertices from the whole graph, we get the same number of components, because there won't be any other edges joining the components. Otherwise the vertex should be in the set. And now there's in need of a little bit of counting how many components we can get, but yeah, the result is this one. Yeah. So because you can try it for k equal to 3, and if you remove a set of vertices of degree 3 from a tree, you can get at most k plus 2 components if you count it, like the worst case. So yeah, so that's the sketch of this proof. So we have this sufficient condition for existence of a k tree with a toughness. So how can we use this for k walks? Oh, we can use it quite easily, and because in 1990 Jackson and Wormal proved that if we have a k tree, if G contains a k tree, then we have a k walk, and if we have a k walk, we have a k plus 1 tree. I know is it obvious how you can do it? Because if you have a k tree, then let's say we've got something of this small example, how we can get like you have 3 tree, how you can get a 3 walk. It's really the easiest way how we can look on it. Just take this tree, double all edges, then you get a graph such that degree of every vertex is even. Take an Euclidean trail which goes through every vertex at most, like the degree divided by 2. So in this case, at most 3 times. You get a 3 walk. The second implication is to prove is done by induction, but if you can have a look, you have a 2 walk, then from the 2 walk you just remove, if you have a cross, if the 2 walk crosses itself, you just remove one edge nearby, and and here as well, what you get is a k plus 1 tree. So therefore, just combining the previous two theorems, we have a sufficient condition for the existence of a k-walk, and it says like if the graph is 1 over k minus 2 tough, we have a k-walk. But it works only for k greater or equal than 3. So that's from these guys. They also conjecture, when you see this corollary, that it might be improved for just by 1 down here. That still it's open whether if the graph is 1 over k minus 1 tough, whether it has a k-walk. So it still can be improved.
So it's open for any value of k?
Yeah. 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 And you can't have it down here 1 over k only because there are counterexamples, which I will get maybe to them later. So we have this. So we restrict to ourselves for k equal to 2 because this theorem doesn't tell anything about two walks. So what is known about two walks is this. These two guys in 2000 proved that 4 is enough for the existence of a two walk, which is quite high toughness for existence of a two walk. Of course, it's not the best result. It really can be improved because they also try to find lower bound, and what they found a graphs with containing no k-walk and has toughness this number. For example, for Hamiltonian cycle, you get a 9 over 4, I believe, 9 over 4 for tough graph with no Hamiltonian cycle. For a two walk, I think it's 17 over 24 or something like that. But definitely, like for a growing k, this fraction goes to 0. So, but you can see like there is still quite a huge gap because it's known for that the 4 tough graph has a two walk, but there are only no graphs which are 17 over 24 tough, which doesn't have a two walk. So the gap is quite big. So, yeah. And maybe, yeah, this was proof as similar to the K trees, but the only difference they did, because it's known that if the graph is 4 tough, then it's 2 tough as well. And if the graph is 2 tough, then you have a 2 factor in the graph. It was proven, and what they only did, they took a 2 factor of a graph, so it's a collection of cycles, and they just want to connect these cycles into a connected graph such that what they wanted to have the maximum degree at most 3 here. If you are able to do it, like for example, like this is, you can't do this one because this vertex would have a degree 4. So this is okay, and let's say this is okay. So if you are able to prove that you are able to connect these cycles into a connected graph, then you can get two walk easily because you just double these edges which are not in the two walks. You get again Eulerian graph with maximum degree 4. You have a two walk. So, but for proving that there is enough number of these edges, they need the graph to be 4 tough. Yeah. So that's it. So let me now just move to a Chordal graphs because, yeah, like in the general case, it's hard to prove for the two walks or for the Hamiltonian cycle any good results. So let me restrict to a Chordal graphs. So Chordal graph is that every cycle of length greater than 3 has a chord. It's one possible definition of Chordal graph. So if you have a, let's say, 5 cycle, then there must be these 2 edges, otherwise you would have a big cycle. So this graph with these 2 red edges is a Chordal now, because there is no C4 which wouldn't have a chord. Now it has. And if the graph is Chordal, then what is the simple shear vertex? Yeah. Simple shear vertex, it has a complete neighborhood. And it's well-known theorem about I think it's due to Dirac that if the graph is chordal, then it has a simplicial vertex, and you can remove it and the graph still will be chordal. So you can construct a chordal graph such that you just will add new simplicial vertices into it just by reversing this one. So what is known about chordal graphs? So for Hamiltonian cycle, in 1997, Chen and some other guys proved that 18 tough chordal graph is Hamiltonian. But yeah. So at least it's a result with a toughness that proves there's a Hamiltonian cycle. But imagine the 18 tough chordal graph is really, it must be really a big one, because if the graph has is 18 tough, then it's 36 connected, so it will be a really big one. So, yeah, but at least it's a positive result. So, yeah. And I think it was Bohemia and Harand and Kach, these three guys, restrict to planar graphs. So, and they were able to prove this nice theorem that every chordal planar graph with a toughness greater than 1 is Hamiltonian. So if the graph is planar, the situation is much better, because the necessary condition for Hamiltonicity is that the toughness has to be at least 1, and if it is greater than 1, it's Hamiltonian. So it's a good one. So, and moreover, they were able to find chordal planar graphs with toughness equal to 1 with no Hamiltonian cycle. So it's sharp. So maybe I'll show you the proof, because it's very simple, and because what I did later on is that I tried to prove something similar for K-walks in my particular 2 walks, but yeah, my proof was, let's say, quite long, but was based on this one. So I will show you just short proof of this one. So first, if you take a chordal planar graph with this toughness, then it's planar, then degree of every simplicial vertex cannot be greater than 3. Because if it's 4, then you get a K5 in the graph, and it's not planar. So it's at most 3. Yeah. But if the toughness is greater than 1, this implies that the graph has to be 3 connected. It cannot be 2 connected. So degree of every simplicial vertex is exactly 3. So, and now it's quite handy. So you can construct this graph by adding only simplicial vertices of degree 3. And if you will do it somehow in clever way, then the clever way, I mean that in one step you won't add one simplicial vertex, but you will add all simplicial vertices into a neighborhood of a simplicial vertex in the graph. You don't need to add all 3 vertices, but if you will add, let's say, these 2 vertices here, then later on you can't add this one, because otherwise you would add this with these 2. So we will just somehow group these adding of these simplicial vertices into this graph. Yeah. So one easy observation, then in one step you can't add these 3 vertices, because assume this is not the whole graph, that there is something rest, then if you remove the black vertices, you get 4 components. You get these 3 isolated vertices and the rest of the graph. So this cannot happen. So in one step you can add only 2 simplicial vertices into a neighborhood. So now assume, prove by induction, assume there is a Hamiltonian cycle in the graph. So it goes through a simplicial vertex, add 2 vertices at most into neighborhood, and just simply locally extend the Hamiltonian cycle. So it's very easy. So because this proof was so simple, I tried to prove something similar for a 2-walk. Because for 3-walk, the result by Win is really almost sharp, so there won't be any chance for improving. But for a 2-walk in chordal planar graphs, I got this one. Yeah. Yeah, the proof was similar, but there were much more cases than in here, because if the toughness is 3/4 or greater than 3/4, then you can have simplicial vertices of degree 2 and 3. And you just check some combinations and prove that in every step you can extend a 2-walk on the new vertices you just added. So, but it's not quite simple. There are quite a few options. But let's say it's a positive result. Then what we did with Zdeněk Dvořák and Daniel Král, that we assume that, okay, so in this case, the simplicial vertices could have a degree 2 or 3. Okay, so let's say, just forget the simplicial vertices of degree 3 and assume you have a simplicial vertices of degree 2. So what you have, it's two connected, so you have a simplicial vertices of degree 2. So it's a class of graph of 3 with 2, or you can describe this graph in a different way. And we tried to prove existence of a two-walk. But during the proof, somehow we realized we don't even need the chordality of the graph. So therefore we changed the class of the graphs we are working with, and we took the K4 minor 3 graphs. But I won't define this, because this class is the same as the serial parallel graphs. Do you know what is serial parallel graph? So serial parallel graph is just, you can construct this graph by two ways. So you've got a block with two poles, and the simplest block is an edge. So you may start from an edge. And you've got two options. If you have two blocks with two poles, then either you can connect them by serial join, which is that you identify, or let's say this vertex and this vertex, you get this. So this is a serial join. Or you can use parallel joins. So if you have a two block, you identify this vertex with this one and this with this one, you get this one. So you got these two ways of joining two blocks. So what you get is a serial parallel graph. And because it's two connected, it's the same as K4 minor 3 graphs. So, and we are able to prove that 4/7 is enough for existence of a two-walk, like greater than 4/7. And we found a graph which are 4/7 tough and has no two-walk. So let's say it's sharp. So this is this example. Moreover, you can see that this graph is chordal, because if you take a block of these graphs, then every block is, these two poles are connected as well. So this is chordal as well. Yeah. But you can do like non-infinite classes or infinite set of graphs which doesn't have which are with the same property, are 4/7 tough and has no two-walk. So it's not just this one graph, but there are infinitely. I believe. Yeah.
Is it by computer search?
Yeah, but the proof is not by computer, but
described by computer search.
Yeah. So that was about two walks. So, and the last chapter is about Trestles, and at the end I will show you the relationship between Trestles and K-walks. So again, it's a generalization of Hamiltonicity, because like Trestle is a two connected graph with maximum degree at most this R. Okay, so if R is equal to 2 in this case, it will be a Hamiltonian cycle. Because if the graph contains a two trestle is two connected subgraph which contain every vertex and has a maximum degree 2. So it's a Hamiltonian cycle. So this is example of a three trestle in a graph. And what I will need, you probably know what is K1R. And if I say if graph is K1R free, it means that it doesn't contain K1R as an induced subgraph. So you know what is induced, probably. Yeah. And sometimes K13 is called claw. So if I say claw, it means. So first, what we did with Roman Kužel, because like the Trestles hasn't been studied so much, so there is lots of works to do. So first we asked, well, is it NP complete to decide whether a graph has an R trestle? And answer is yes. But yeah, how we prove it? Yeah. So we reduce this problem of an R trestle to planar Hamiltonian circuit problem, which is the following. You get a 3-connected cubic planar graph, and it's NP-complete to decide whether it is Hamiltonian or not. And we reduce this one to a finding an R-Tressel. So what we actually did, we took this 3-connected cubic graph. From this graph, we made a new graph. I will show you how, such that the original one has a Hamiltonian cycle if and only if the new one has an R-Tressel. So what we did, every vertex replaced by this guy if R is odd, and by this guy if R is even. And the size of this set is this one. It depends on the R. And similarly here, size of this set and size of set A and B depends on the R. If this is even, if this is odd. Why we just took this graph? Because if you go through it, then if you just want to find and just for it will be replaced, every vertex in the cubic graph will be replaced by this graph, and these are the 3 attaching edges. So actually what we did, the size of this set especially is set such that if you want to try and, in this case, 3 trestle, then always like one attaching vertex must have a degree 3 and the other 2 will have degree 2. So there is one connection left to connect it with the other guys in the graph. And it's symmetric, so you don't care like from which side you go to this vertex. And this is similarly for even R's. And you just, so why, like if the original graph has a Hamiltonian cycle, then the new one will have an R-Tressel because, you know, this Hamiltonian cycle went to this vertex, let's say this way, and left this way, but you can find always an R-Tressel in this way. And the opposite implication is that if you have this guy in this new graph, then you try to find an R-Tressel, but you always, like in this guy, one of the vertex has degree R and the other has degree R minus 1, so therefore only 2 edges attaching this guy in the graph are used. So therefore if you contract this whole guy to a single vertex, you get a vertex of, like, in the subgraph you get a vertex of degree 2, and that's the Hamiltonian cycle. So yeah, that's the NP completeness. So now move on again to the toughness. For the toughness, there's similar necessary condition for the graph to have an R-Tressel, and it's similar, it's differently written, but again, if the graph has an R-Tressel, the toughness has to be at least 2 over R. And for the 2 walk, it was 1 over K. In this case, it's 2 over R. And the 2 is there because, like, the trestle has to be 2 connected. So therefore, instead of 1, now it's 2. And the proof is similar. And there is this general open conjecture, which is still open for every R, which tells us that there exists a toughness, depending on the R, such that the R-tough graph will have an R-Tressel. So it's open for every R, and so, yeah. I tried several times to prove it, but didn't succeed. So, but yeah, it seems like obvious that it will be true for some R's, and yeah, but it's hard to prove it. It's like for the K-walks, it's simple because K-walk, like in general, is only 1 connected, so you can use the result for trees. In this case, you need a 2 connectivity subgraph, 2 connected subgraph. Also, it's much more difficult to handle it by. So this is open conjecture. So what is known regarding the toughness? So what we did, we tried to find graphs which has a, let's say, quite high toughness, or they are at least this number tough, and has no R-Tressel. So let's say lower bound on this number, like where can we go, like lowest possible. So what we did, we were able to find graphs which are this r square plus r plus 1/2 divided by r square tough minus epsilon, and has no R-Tressel. And actually, like when when I prove it, I was quite surprised by this number, because what is interesting that for arbitrary r, this is all the time greater than 1. So let's say if for arbitrary r you are able to find graphs which are more than 1 tough and has no r trestle for arbitrary r. So you can't go with the toughness below 1. So yeah, I still have a time, so maybe short notice about the construction of such a graph. It's similar to which was used for K-walks and Hamiltonian cycle. Just depends on to find a nice suitable, like let's call it base graph, and the construction is the same, similar for Hamiltonian cycle and K-walks. So this is my base graph. So this is let's say clique of size 2r, and I've got these two special vertices u and v, which are attached by a path of length 2. In general, this path can be longer, but we don't care much. And we define graph with these parameters as follow. We take m copies of this guy, and in these are copies, let's say L1 to Lm, and in each copy of this guy we have these special vertices u and v in the original, but in these copies it will be u1 and v1 and u2 and v2, so on. And so between these vertices we add all possible edges between like this copy of this base graph, and then we take a clique of arbitrary size, let's say of size L, and we put all edges between this clique and the rest of the graph. So we get some graph which will maybe more picture. Can I use this one for blackboard? Yep. So we have these small guys down here, and there is m copies of it. You've got a big clique of size L here, and we add all edges here, and we've got these u and v vertices in every copy of the base graph, and between these special vertices we put all possible edges between these vertices. So this is the graph. So first, this graph shouldn't have a r trestle if m is greater than L times R plus 1. Why? Because if you look on the base graph, then let's say for 3 trestle it looks like exactly like this. Then if you have a 3 trestle in this graph, then degree of this vertex is 3. It has to be the same for the v. So if you want to construct a 3 trestle, or in general r trestle in this graph, then all these vertices already have degree exactly r. So, and you want to connect in between these vertices. So the only way how to do it is that you have to use edges going to the clique KL, and you have to use, like in one case you have to use at least 2, because it has to be 2 connected, and if the m is greater than L times R plus 1, then there is not enough of these edges to join it. Yeah, there is one special case which I might mention, because otherwise there would be like 2 times L plus times R, because what you can do, just show, I will, because, so, this is the, and it continues. What you can do, because one case is, if you will, just one edge will go into this vertex, then you don't need this edge, because this vertex is already connected, and you can use this vertex will be free, because it will have a degree r minus 1, and you can connect it here. Still the degree here is r, here is less than r easily, so you can use one edge to connect it. But you can't do it for both vertices here. So for every guy in the worst case, you need at least one edge to connect it with the creek up here. But you know, there is not enough edges either. Yeah. Because you've got m copies here, a number of edges going from this creek is L times R, because it's an R trestle. And it's, if the size is +1, so you can't get it. On the toughness, you can count the toughness, but yeah, I won't go it. So the toughness will be this number depending on the L and M. And if you put here the M is greater than L times R plus 1, and then you set the L is going to infinity, then you get this fraction. So that's it, this one. Yeah. So that's the only result regarding toughness in R trestles I know, yeah, at the time. So the last what I want to talk is in 2004, Riacek is my boss and Kaj is another guy from Slovakia. They proved that every two-connected claw-free graph has a 3 trestle. Claw-free is K13 graph, so because I didn't mention it for K-Volks. For K-Volks, it's true that if the graph is K1 K, let's say, then it has a K-1 walk. It's really easy to, because let's say if the graph is claw-free, then the graph has a 2 walk. It's very easy to prove it. And so these guys assume that it might be true for the trestles as well, but they were only able to prove it for R equal to 3. And luckily we were able to prove it for every R in a way such that if the graph is 2 connected and K1 R3, it has an R trestle. So, and it works for every R, even for R equal to 2, but it's not that interesting because if R is equal to 2, it's Hamiltonian cycle. But yeah, you know, K1, 2, 3 graphs is the only complete. It's the only complete graph which has satisfied this. So it's true as well. So yeah, what else? Like, yeah, we proved this one, and somehow, in some sense, this theorem is sharp because this example is, you can see, this graph is K1 R3, and so it has an R trestle, but it has a no R minus 1 trestle. How to prove? Yeah, because you've got this set of vertices of degree 2, so clearly the degree of this vertex must be at least R minus 2 because of this number of edges, the same as here, same as here, same as here. But then you want to connect these 3 blocks into a two connected graph. At any vertex you have to use 2 edges here. You cannot use only 1 because it's odd cycle here. So therefore there is an R trestle and no R minus 1. Oh, maybe. Yeah, the proof, yeah, I'll skip the proof. But so that's the idea. The idea of the proof is really simple. Like, you guys just taken maximal subgraph such that it's 2 connected and has a maximum degree R. So it has, let's say, sub R trestle. So if you are proving by contradiction, not all vertices are contained, so something outside. This is my sub trestle. So there is this vertex connected to outside, the same. Again, degree of this vertex must be, if you set these conditions, then degree of this vertex must be R in the trestle. But the graph is K1R, so in the original graph there must be an edge, let's say this one, and just if the degree of the trestle of these 2 vertices is less than R, then you can add this edge and remove one of those. You will lower the degree of this vertex. You can add this as well, and so again, not to be true, these vertices must have a degree R as well, and you can arguing and keep going, but what we proved that you have to stop somewhere, and if you stop somewhere, then you identify edges of the trestle and edges of the original graph which you will switch, and by the switching you decrease the degree here, you get a contradiction. The only way you have to be careful is that after the switching it remains 2 connected, and after the switching the degree of y will be the same. You won't increase the degree of y, otherwise you'll be just in a circle. So you decrease the degree of x. The same you can do for y. If the degree is r, you can decrease the degree of y, connect something else to it, got a contradiction with the maximality. But yeah, so that was this one. Yeah, and that's my last slide. And connection between Trestles and, is it? Yeah, is it like, yeah, first, like when we proved the previous theorem, we were able to derive a polynomial algorithm from it. So in K1 R3 graphs, we are able to find an R-trestle in a polynomial time. In general, it's NP complete, but if it's K1 R3, it's good, we can find it. And yeah, the connection between R-trestles and walks is this one, because I think it was Tomáš Kaiser, Roman Kužel, and two guys from Paris. I don't remember names, but originally they are from China. So it's Haoli and some other. They prove that if the graph is bridgeless and maximum degree is delta, then you get a delta plus 1 over 2 and like the nearest upper integer walk. So yeah, if you have this one, if the graph is too connected, then if you have an R-trestle, it's too connected, so of course it's bridgeless, then you have a, and from R-trestle you can get this R plus 1 over 2 walk. And of course it doesn't work the opposite way, because from a K-walk you can't do an R-trestle, because K-walk in general, like, it doesn't have to be too connected. So this is just corollary of this theorem and the previous one, because if you put it together, then you get this result, which might not be so interesting for you, but for me, because when I was reading Jackson and Vorman paper concerning K-walks, they prove something similar, but we are able to improve it because we get something better than these guys. So yeah, and that's all from me.